Let's work through an example of computing a vector surface integral f dot ds over a surface M. The vector field in this case is given in coordinates as follows. So it's f of xyz equals yz comma xz comma xy. So this is a vector field defined on all of R3, in fact. But we're really just restricting our attention to the surface M, which is the graph of z equals 1 minus x squared minus y squared over the unit square, where x and y are between 0 and 1. So M is shown here, where both x and y go from 0 to 1. And so we get this portion of the paraboloid that sort of opens downward. And to compute the surface integral, what we really want to do is use a parameterization, r of uv. And the way it works out is we get the integral over the domain of the parameterization of f of r dot, and then this normal vector r sub u cross r sub v dA. So again, we use a parameterization to rewrite this vector surface integral as a double integral of a scalar function, because I'm taking the dot product of two vector fields. Now, it's important to remember that conceptually this represents the flux of the vector field f through this surface. And what's going on here is if I have this vector n, which is a normal vector, and at the same point I have the vector given by the vector field f, what I'm really doing with this f dot ds, vector ds, is I'm taking f dot n, the scalar ds. Okay, so what I'm really integrating, this can be rewritten as a scalar surface integral of f dot n ds, and then the formula we get here is just the standard process of converting this function over to a function of the parameters u and v, and rewriting our scalar surface integral as a double integral. And just it turns out that this is the way it will work out every time for any parameterization. Okay, so we want to parameterize this, and again, it's the graph of a function, so I can just use the standard graph parameterization. So instead of u and v, I'm just going to call the coordinates what they are, which is really the x and y coordinates, and I get x, y, and then 1 minus x squared minus y squared, because that's what z is equal to. Now, the domain D is the unit square 0 to 1 cross 0 to 1, because those are the bounds for x and y that were given in the problem. Okay, so we need this vector field r sub x cross r sub y, and it works the same way every time. So we could compute r sub x and then compute r sub y and then take the cross product, but at this point we should just remember that this vector is always equal to negative the partial derivative of this function with respect to x. So the partial is negative 2x, so I end up with a positive 2x, and then negative the partial derivative with respect to y, which is positive 2y comma 1. All right, so you can derive this on your own by just taking the partials and then taking the cross product, but this is just a time-saving aspect if we can sort of memorize this formula. Okay, so we have this vector field in terms of x and y, and then now we want to plug the parameterization into f. So f of r of x comma y basically just means plug in z equals 1 minus x squared minus y squared into these formulas. So we get, I'm going to start it on the next line. So we get y times, and then 1 minus x squared minus y squared, and then x times 1 minus x squared minus y squared, and then xy as the third coordinate. Okay, so we've plugged the parameterization into our vector field, we've computed this normal vector field, and so now we can go about this process right here. So we rewrite this, and we have the integral 0 to 1, integral 0 to 1 from the bounds, the domain of the parameterization, and then I have this dot product with this. So I get 2x times this, so I get 2xy, and then 1 minus x squared minus y squared, and then I get 2y times x times 1 minus x squared minus y squared. So that's also equal to 2x times 2xy times 1 minus x squared minus y squared. so I can just make this a 4. So I get 4xy times 1 minus x squared minus y squared. And then the product of the last components is simply 1 times xy, so I get xy. And then if we take this dy dx. Okay, so now we have this double integral that we have to compute. And I think I'm going to split this up in a slightly different way. So I have 4xy times 1 right here, and plus xy is going to give me a 5xy. So this term times this plus this is a 5xy, and then I get minus, and then 4xy times x squared plus y squared. So I multiplied this through times these last two terms and factored out the negative 1. All right. Okay, so now we'll integrate this with respect to y, and we get 5x times y squared over 2, evaluated 0 to 1, and then minus, and then now we have this with respect to y, so I might rewrite this as minus 4x cubed y minus 4xy cubed. And so we get minus 2x cubed y squared, and then minus xy to the 4th over 4 but times 4. So just minus xy to the 4th, and I still have this integral dx. This has to be evaluated from 0 to 1. Okay, so here we just get 5x over 2, and then here we get minus 2x cubed and minus x. So now we're back down to a single variable integral, and so we're going to get 5/4 contributed from this term, x squared over 2 evaluated 0 to 1, and then this is going to become x to the 4th over 4, so that's going to contribute a minus 1/2, and then the minus x is going to be minus x squared over 2 evaluated 0 to 1, which is another minus 1/2. Okay, and so in the end I get 5/4 minus 1 is equal to 1/4. Alright, so in the end we took the vector field F and the surface M, and we used this parameterization of the surface to compute the normal vector and to plug into the vector field, so that we can rewrite the vector surface integral as a double integral, which is shown here. And then we just use some basic techniques from double integration to compute that this double integral is equal to 1/4, and therefore this vector surface integral is equal to 1/4. And this is the method that we'll use pretty much every time we want to directly compute a vector surface integral. We parameterize the surface and then follow this standard method.